Hi, this is my video number 7. I'll talk on the equation of line and plane. Yeah, equation of line in plane. Equation of lines in and plane. Okay, first equation of line in 3 dimension. Equation of line in 3D. Alright, okay, so let's say we have consider 3-dimensional Cartesian coordinate xyz, and we have a line, a straight line, let's call this line L, where on this line we have a point P0, X0, Y0 and Z0, and we have another point, let's say P, any point X, Y, Z. P0 is a specific point, and P any points, where P0 and a point P on L. Okay, and we also have a vector parallel to that line. So let's call this vector V, with component V1, V2, V3, and let's call this vector, and we have a vector position. That's vector position. It should be a straight line, yeah. Vector position. Let's call this R0, and another vector position. Let's call this vector R. So vector position R0 is a vector position for P0. R is vector position for P, and we'll call this vector as vector A. Okay, so vector A is parallel to V, and we have a point P0 and P on L. So we have since vector V parallel to line L, so we have, and R0 is a position vector OP, and R is a vector OP0, yeah? OP. So we have here a vector R. You can see vector R here is R0 plus vector A. So vector R is a vector R0 plus vector A. And since A parallel to V, vector V, so there exists some scalar T such that A equal to TV. That's the properties of the parallel vector. AV is a parallel, then we have a vector T. So therefore, if you substitute into there, so therefore we have R is equal to R0 plus TV. So this is, we call it as a vector equation of line L, yeah, vector equation of L. Okay, so if you look at this T here, for each or for different value of parameter T, yeah, different value of parameter T, so that will give the different position of vector R. So for example, for T equal to 1, you might have here. For T equal to 2, you might have somewhere here. For T equal to 3, you might have somewhere here. Yeah, so there's a different value. So let me write those things. for each value of parameter t, give the position vector r of a point on L. Okay, let me give an example. Of course, from this relation R naught and t, if we consider those position vector, our vector R is basically a vector component x, y, z, and vector R naught is x naught, y naught, z naught. Okay, with V, as we mentioned here, V is V1, V2, V3. V is V1, V2, V3. Of course, we can write this equation as our R is x, y, z. Yeah, our x is x, y, z, equal to R naught is x naught, y naught, z naught, and then our t and v is v1, v2, v3. Yeah, if you equate the same component of each these vectors, so what we have is that x is equal to x naught plus t v1, y is equal to y naught plus t v2, and z is equal to z naught plus t v3. A parametric equation of a line L. Yeah, parametric equation of line L. Now, let's look at the example. Two lines. That's let's say L with x equal to minus 2t, y equal to 3 plus 2t, and z equal to 5 over 2 minus t, and another line, let's say M, with x equal to 2 plus t, y equal to 1 minus 4t, and z equal to minus 4 minus 1.5 t. Okay, 11 over 2 t. So if you look at this equation, is of this form, right? As I mentioned earlier, of that form. So we have x naught t v1. So we can identify or recognize instantly that the point 2, 3, and 5 over 2 lie on L, and point t, 1, and negative 4 lie on M. So let me write those things. So 2, 3, and 5 over 2. Okay, this is on L, and 2 point, yeah, 2, 1, minus 4. Right, this is on M. And as well as if you look at the vector here, this is the vector. That's okay. So the vector, let's call this V1. Let's call vector V1 with component minus 2, 2, and minus 1. This is parallel to line L, and vector 2. Look at this vector M, line M. So we have 1, minus 4, and minus 11 over 2. So 1, minus 4 and minus 11 over 2. This is parallel to line M. Now, how to show that? Okay, are these two lines intersect? So the question is intersect. Intersect. Okay, are these two lines intersect? So now let me pose this question to you. Are two lines which are not parallel, always intersect? Okay, that's the question. Are two lines which is not parallel are always intersect? So if you have a line, let's say this is a line L, this is a line M. Okay, so if you look at in two-dimensional case on XY plane, for example, of course these two lines L and somehow they will intersect. But if you look at in more bigger picture, that three-dimensional case, for example, if the line L and M lies on the two different plane, then definitely L and M are not intersect. So it is possible that for the line L and M are not intersect. It is possible. Okay. So in order to show this, let's consider S as a intersection point. So let's say this point as S. Okay, let S be the intersection point. Intersection point between line L and M. So what does it mean? So it means that points X, Y, Z for L, or I can and point X, Y, Z for M are the same. They should be the same. So which means we have a point X for L is equal to point X for M, as well as a point for Y for L is equal to Y for M. You might have different times. I put T here, which means you may consider two objects. You may consider two objects that move along L and move along M from somewhere. Of course, this object that move on line L will reach S at different time than object through M reach the point S at the different time. So that's why we use TLTM, TLTM. Okay, so if you have this in mind, so which means we have all right, for L and X for M, so we have 2 minus 2TL. This is equal to, I just change that. So for L, T, I use T as a TL here. TTL, which means line on line L. And for TM, we have 2 plus TM, 2 plus TM. Okay, and for Y, so for Y, we have 3 plus 2TL. This is equal to 1 minus 4 TM. Of course, from here we have two unknown TL and TM, and we have two equations. We need to solve these two equations. Okay, solve these two equations for TL and TM. So if you solve that, so you have TL, this is equal to 1, and Tm, this is equal to -1. This is not difficult to solve. It's just a 2 by 2. Okay, and also we should have Z. Just a minute. My telephone ran out of battery, so let me adjust that. Okay, so we also have Z TL must equal to Z TM. Okay, so from here we have ZTL. You take from those, so ZTL give you ZTL, that give you 5/2 minus our TL is 1, minus 1, so that give you 3/2. And ZTM, which is -4 minus 11 minus 4 minus 11/2 TM. Our TM is -1, so that we have plus x 3/2, right? So they are equal. So we can see here ZTL is equal to ZTM. So therefore the line L and M are intersect. Okay, if ZTL and TM are not the same or have a different value, then the line L and M are not intersect. In this case, they are equal, so they are intersect. Okay, you can try. Let me give you an example. You can try this. It's an exercise. Show that the line that passes through the line that pass through points -1, 0, and 1, and 1, 1, -1 does not meet. We call this as a skew line. Skew lines. And not parallel as well. And not parallel. They are not meet and also not parallel. With the line passes points 1, 3, -1 and 1, -3, 2. So you have two lines here. Let me sketch. So you have two lines. One line is passing through this point, -1, 0, 1, and another passing through 1, 1, -1. And you have another point here, another line which passes through 1, 3, 1, 1, 3, -1, and let's say 1, -3, 2. Okay, show that these lines are not parallel, so it's not difficult because you can check the vector for these two, all right, for this line, and check the vector for this line. You can find those things. It's not difficult because the 2 point given, and also to show that those lines are not meet or not intersect. Okay, follow the example given here and check for the third point. If the third point are equal for each line, then they are parallel, they are intersect. If not, they are not intersect. So next we look at the angle between two lines. Angle between two lines. So let's say we have a line M and line L with M U, vector U perpendicular to line M, and vector V, perpendicular, parallel to line M, and vector V parallel to line L, with the angle in between theta. Okay, so U parallel to line M and V parallel to line L. So from there, you can find those theta using the dot product. So we have U dot V. This is vector U V cos theta, and hence from there you can find theta is the inverse of cos U V U V. Okay, I give you another exercise here. Prove that the parametric equation of L, the parametric equation of L can be written as we have x minus x naught over v1 equal to y minus y naught over v2 equal to z minus z naught over v3. So this we call it as a symmetric equation of L. Symmetric equation of L. So it's not difficult to prove, because from the parametric equation, what is parametric equation? We have x equal to x naught plus tv1, y is y naught plus tv2, and z is equal to z naught, y naught, z naught plus tv3, where point x naught, y naught, z naught is on the line, and the vector with component v1, v2, v3 is parallel to the line. All right, another exercise for you. This is number 1. Then this is number 2. Find the parametric and symmetric equation. Yeah. Find the parametric and symmetric equation of line L that passing through a points, let's say A 2, 4, -3, and B 3, -1, 1. Alright, so let's call this part A, and part B. At what point, at what points does this line intersect? Intersect the XY plane. Yeah. if you can visualize this, if you consider in three-dimensional, so we have plane xy and z, and this line is somewhere, let's say like that. So obviously it's somehow it passed the intersect with xy plane. So we need to find what is the point here. Okay, it's not difficult to find. Just you got the parametric equation on xy plane. Z is 0, so from this equation z0 you can find what t is. So use that t in x and y, then you can find those points. Okay, and give you another question. If the line L passing through P naught with point x naught, y naught, z naught, and a point P1 with x1, y1, z1, show that the symmetry equation of L is given as x minus x naught over x1 minus x naught equal to y minus y naught bahagi divide by z minus y minus y naught, y1 minus y naught equal to z minus z naught over z1 minus z naught. Okay, so we have 3 exercises for you to do. Okay, so next I'll give you how to find the distance or the shortest distance from a point to a line. Shortest distance from a point to a line. So, okay, a distance from a point to the line. So what this means, if you have let's say this is our line L, we have a point, let's say S here, and then we need to find what is the shortest distance from S to that line L. Of course, the shortest distance is the distance that make parallel to the line L. Okay, so let's write this as a theorem. So let L be a line that passing through P, passing a point P, and parallel to a vector V with component V1, V2, V3. Okay, then the closest distance from a point S to L is given as, so let's call that D as a PS times V over magnitude of V. So we try to visualize this. So a point, because P or line L passing P, so I can put P anywhere here on the line. So that's our point P. And from there, and also we have a vector V that parallel to L. So we have our vector V is here. That's vector V. And of course, from these 2 points P and S, we can form a vector. You can form a vector there. So this is your distance, the looking distance, and let's say this is the angle theta. So from the diagram, of course, it is we can see that the ds. So let's say this point SQ. Okay, this point, the S projected on line L. So we can have from there, from figure, so we have D is that SQ, right? The SQ is we have vector PS sine theta. Okay, and then you can write this as a PS sine theta times vector V, magnitude of V, and divide again with magnitude of V, with magnitude of V is different than 0. So therefore, we have from there, rearrange those things. So we have PS V sine theta over V, that give you PS times V over V, magnitude of V. So with this formula, given any line L, given any point outside of L, let's say this point S, we can always find the closest distance between those points to the line. Okay, so let me give you example for that. Example, find the distance from a point S 115 to line L, given as x equal to 1 plus t, y equal to 3 minus t, and z equal to t. Okay. Solution. So we have a line L, we have a point P, and we have a point S here. Our point S is given as 115. From the given line equation here, we can recognize instantly that the point 1, 3, and 0, 1, 3, and 0 is on L. So let's call those points as P. So this P is 1, 3, and 0. And also from this line, we can determine V, where V is 1, minus 1, and 2. 1, minus 1, and 2. Okay? Because from the equation of from the parametric equation of a line, we have x equal to x0 plus t v1. So v1 is the component vector that parallel to the line. For this, we have y0 minus t v2, z equal to z0 plus t v3. So v3 here is 2, v2 here is minus 1, v1 here is 1. Okay, so having done that, okay, alright, so from there we can find vector PS. Yeah, we can find vector PS. Our PS is 0, -2 and 5, and we have vector V there, so you need to find what is PS cross V. So this is I, J, K. PS is 5, -2 and 5, and our V is 1, -2, -1 and 2. Okay, so you can find this for component I. So we have -4 plus 5, so that gives you 1, right? So I can write this like this, just this is I, yeah, 4 minus so plus 1, -4 plus 1 plus 5, you got 1. And for J you have minus and 0 minus, so you got -5 J, and for K you have 0 plus 2. Okay, so we have I plus 5J plus 2. Okay, and then from there you can find what is the magnitude of PS times V. This is 1 plus 25 plus 4, so that gives you 30. And magnitude of V, this is 1 plus 1 plus 4, that gives you 6. So therefore the distance L is PS times V over vector of magnitude of V, that gives you 30 over 6. This is, you can write as a 30 is 6 times 5 over 6, that gives you 5. Okay, and also we can have the shortest distance between two lines. Yeah, the shortest distance between two lines. Let me explain how to do it. Yeah, find the shortest distance between two lines. So we have L. Let's say this line L equal to 1 plus T, Y equal 3 minus T, Z equal to 2T, and line M as X equal to -3 plus T, Y 1 minus T, Z is 1 plus 2T. So if you notice that these two lines are parallel, because those vector, we have 1, 1, -1, you have 2. So line L and M are parallel. So how to deal with this? So we have a two parallel line, L and M. We want to find the closest distance between these two lines, so which means we want to find the line that perpendicular to each other. So this perpendicular to M, this line also perpendicular to L. So this is the distance, the distance that we are looking for. So of course from that line we can let's identify the vector V. Our vector V is 1, -1 and 2. Okay, and then of course from that point, from those two lines, you can identify the point on each of those lines. So for example, on line L, you can identify this 1, 3 and 0. Let's say those points are here. 1, 3 and 0, and for this you have -3, 1 and 1. So let's say this point are here, -3, 1 and 1. Okay, let's give a name. Let's say this is P, this is Q. Now, having obtained this point, we got this point, you can form this vector. You can form this vector, that PQ. Okay, having done the vector, find the vector PQ, you can cross product with V and then find the magnitude, and therefore you can find the distance. Okay, so I leave it to you as an exercise. Do it yourself. And I give you exercise, another exercise for you. Find the distance. Find the distance between point T 1, 10, minus 10 and line L and line L that passing through points P 1 to 1 and Q half minus 3 1 over 4. Okay, I leave that couple of questions to you to do as an exercise. Okay, let me wrap what I have talked in this video. So we deal with the equation of a line on the space, three-dimensional space, where we consider as a Cartesian with Cartesian coordinate x, y, z. Okay. I also showed to you the parametric equation. Give you the parametric equation of a line, the symmetric equation of a line, and the vector equation of a line, the angle between two lines, the shortest distance from point to line, from two parallel line as well. Okay, so with that, I thank you. We'll meet in the other video. Bye.